Hello everyone, welcome back. So in this video we are going to do the deep dive into this problem. So I thought to create another video of this problem because I have not gone through the dry run in the previous part of this video. So I'm trying to simplify this question. So if you are already subscribed my channel, so you should be get benefit of the some extra deep dive and understanding, so you can try yourself, you can understand the code and how we should approach the code, right? So little different I'm trying to do here. Let me know in the comment section that you will like or not, right? So very first, what we will do in this video, we'll try to understand the problem in the form of summary, you can say. Then we'll try to understand the intuition, and then we'll go through the code that we have already done in the previous video. Okay, so we'll understand more, but just try to focus first of all the problem summary and what we have in the intuition, what is our approach, and then we'll understand in the deep dive with the dry run the code. So very first, let's understand the problem, right? So what we have given a tree, as you can see here, right? We have given this tree, and the question is saying that, so we have given this tree that is called nodes, right? So each nodes, we have given a tree with n nodes, we can say, right? And let's suppose these nodes are nothing but n nodes. Can we say that, right? Because as you can see, it is saying we have given n nodes. Okay, and if the tree having n nodes, means these nodes can be either connected and cyclic or acyclic. So this is a cyclic. Understand what I'm trying to say? There is a undirected tree, means directed means undirected means we have two nodes, right? Let's suppose node u we have and node v we have. So if we will connect this node, right? If we will connect this node u to node v, right? So there is direction. If there is a direction, this is called directed tree, we can say. Okay, or you can say directed as we have given, or directed node we have given. Can we say that? Means the tree contains in the directed form. So we can say the tree is connected, directed connected tree, we can say, right? Or graph. But here there is no direction is given. It means it is look like this. Okay, on if there is both side we have direction, means this is bidirectional, or you can say we have direction given. So there is no direction, it means this is undirected tree, we can say. Okay, so it is saying we have given undirected tree with n nodes. So if you have n nodes, it means it is we have given connected, and this tree is, or you can say graph is acyclic. So if it is acyclic, means there is no cycle. Cyclic means, acyclic means no cycle, means it's a tree. If it is cycle, this can make a cycle also, right? Means that can be a graph that can contains a cycle. So a graph and tree, the major difference is that there can be cycle or not cycle. It can be connected or not connected, right? That depends on. So it's a, so you can say tree is also a form of graph, right? Only if it is not connected, right? Just for understanding I'm saying. So we have given zero indexed array. What is the zero index array means? Means we have given array, and this array start from index 0 and it will keep going till n minus 1 edges. So let's suppose we have n equal to how many? 5 edges we have given, means 5 nodes we have given. What are the possible nodes will be there? So if you represent the node can be 0, 1, 2, 3, 4. These are the nodes we have given, right? And these nodes are connected with each other like this. Or this is not cyclic. This is not cyclic. Means this is acyclic. Means we will not make a cyclic. Okay, here. And the nums that we have given, that is our nodes array. All the nodes is an element of the nums. So we can say each index represents a what you call node, right? That is labeled from 0 to n minus 1. So this is nothing but your nodes. Nodes are nothing but the index of array. Are you understanding? So that is why it is saying you have given a 0 indexed integer array, right? And its name is nums, nothing but nums. Can we say that? So it starts from 0, then we'll go to 1, then 2, then 3, and next will become 4. Okay, so this is the what you call nodes, right? Start from 0 and goes to n minus 1, that is 4, and if n is 5. Can we say that? And this is nothing but your nums array. So each nums array contains some value. Let's suppose what are the values are there. So if you'll take 1, then we have 5, then we have 5, then we have 4, then we have 11. Just for understanding, okay? I think I've taken more indexes. Let me clean here, so we'll understand again. Let's suppose I'll start from index nodes. Node is 0, index is 0, 1, 2, 3, and 4. Yes. So it is not required, right? This is n is not required. It will go till the n minus 1. So we can remove that, or you can leave it for now. Okay, so understand what is the node, what is the index. Means the index of the array is nothing but our node, and there are some elements are there. Means this 1, 5, 5, 4, and 11, this is our nums. What is this? This is our num, and these nums at these elements is the value of the ith node. What is the value of ith node? Means there is some element is there. We'll talk more later, just understand here. Then the question is saying that, let me clean all of this. Now the further question is saying that nums at I, which is, you can say where we have here, is the ith value of ith node. Okay, then it is saying you are also given 2D integer array similar to the nums we have of the length n minus 1. Means if there are n nodes are there, means n is 5 nodes, right? If n is 5 nodes, means the nodes are marked as 0, 1, 2, 3, and 4. So these are the nodes, right? And each nodes have some value that we can see in the nums here, right? Similarly, we are given another edges and saying its length is n minus 1. Means length of n minus 1 is what? 4. Its length is 4. Means how many edges are there? 4 edges there. We have 5 nodes are there and 4 edges we have given. From there we can say that nodes are connected, but it is acyclic because there is one edge is not there. So let's understand again. Okay, so let's suppose if I will represent these nodes, right? Again, let's suppose call as a, let's take as 0. Okay, so this 0 we have here. Okay, then we'll connect with 1. So how many we have used? 1 we have already used the edge. Then it will connect to 2. Just for understanding, I'm taking this example. Okay, 2. Then 2 node we have used. Then we have 3. So how many edges we have used? 1, 2, 3. One more is left. So I'll connect with here. And this is nothing but the 4. So this is connected. How many edges? All the 4 edges we have connected, used, right? So if all these edges are used, it means what? This is not connected. This is not forming the cycle, right? And that is why we can say it is a cyclic. I'm just explaining you the question so you can understand, right? How we should understand the given things. Okay. Then we have edge at I is nothing but AI and BI. Okay, what is this AI and BI? Means if we have let's suppose I'll say A and this is B, right? It means if this is node A, if this is node B, means from here to here we are connecting with this edge, and this is represented at here. Okay, that is why it is saying that node edges we have given like this. So if you'll say edges at 0, we have this, edges at b1 we have this, 2 and 3. So if you see here, the very first is 0 to 1, then 1 to 2, then 1 to 3, not like this. We are saying we have to represent it again. Let me show you again. So if you represent this one, right, very first, so 0 to 1, it is saying how this is 0 and this is 1. So these two nodes we have given at index 0, right? So you need to connect it. Then it is saying 2 to 3. So let's suppose you will take 2 here, right? So 2 or 1 and 2 we have to connect, that we are doing at index 1. Then 1 and 3 we have, means from 1 and 3 will take another node here. So this is also connected. Next we have at 3, right? Is at 3 we have 3 and 4. Let's suppose we'll connect like 3 and 4, and that is why this array is this tree is similar to this tree. Can we say that? So we have given this tree, right, and this based on how you are representing this, these nums and this. See, this is our Leetcode, right, and it is showing you the tree. But whenever you will go to the what you call interview, right, you will not see this visualization, and that is why I'm teaching you here to how to understand and to build yourself in your intuition, right? So until you will not understand the question, right, you should understand the question, and the question summary should be in your mind, right? So that while understanding the intuition or explaining the intuition, you should understand what I need to do, what is given, understand? So like this, you just understand that this is not given for you right now, and you are building based on the given things. Like let's suppose the nums we have given, then edges we have given, right? Let me know in the comment section that you are agree or not. Okay, so then what we should do? Okay, very first we have the edges we have given. So as you can see from the edges, what we have made this tree, right? So to make this tree, it means you have to build what? Adjacency list, we can say, right? Means from the given edge you can build the adjacency list. Once you build the adjacency, means the either you can build the graph, you can build the tree, right? Like you can do that, right? So internally in your mind should understand, if we have given the edge, right, so we can build this tree, right? And the nodes we have already given on here, so that is another thing that we will understand later. But for now, you just understand, if we have given the edge, right, you can build the tree. I hope you understand, right? Now think, if we have given these two things, we have given nums we have given, edges we have given, and we have understood till what you call from here to here, right? What are the things we have given? Let's understand further. Next, what we have given is, give me 1 second. Next, we have given is remove two distinct edges, okay, and form 3 connected components. Let me write again. So we have represented 1, then 2, then 0, then we had 3, and then we have 4. Can we say that? So these are we have given, correct? Means if you represent the given edges, right, and if we'll connect all the edges, right, we can say this is our what? Our tree, right? Means our tree is connected with all the nodes and it is acyclic, first of all. Then once we understand, it is saying remove the 2 distinct edges of the tree to form the 3 connected components. For a pair of removed edges, means we have to remove some pair of edges. The following steps are defined. What are the steps are defined? That we will understand later. First of all, understand this line. Means remove 2 distinct edges of the tree to form 3 connected components. 3 connected components, sorry. Okay. Means let's suppose if I will remove some of the what you call edge. Let's suppose I will remove this one, right, and I will remove this one. Okay, you can take any of these 2. I'm just taking for now here. Okay, you can take how you can remove, let's suppose this one, and you can remove this one also. Okay, you can remove, let's suppose this one and this one also. So these are the possibility that you can do. You can remove this one and this one also. Okay, so let's understand that I will remove this part and I will remove this part for understanding. Okay, what are the components we left? So if we'll represent this, right, means we will remove this one and then we'll remove this one. Can we say that? Now you tell me how many components are left there. The very first I can say one component is here, correct? Another component is here. I hope you understand. What is the left one? So the remaining one is this. How many components? Component 1, 2 and 3. Total 3 components left. So that is why it is saying remove 2 distinct edges. Once you will remove 2 edges, right, you can form 3 components here to form the 3 components. So that you understood, right? Now it is saying for a pair of removed edges, right, means the first pair is this and second pair is this. What are the pair that you have removed? Let's suppose this is 1, 2 and 3, 4. Can we say that? So this is called the pair of removed edge, right? This is a pair of removed edges, right, that we have given. So for this you have to follow the steps. What are the steps are there? That let's understand. So can I say the very first step is saying that get the XOR of all the values of nodes for each of the 3 components. We'll take the XOR of these values, right, and then we'll get all the values of the nodes for each of the 3 components. Okay, all the XOR of all the values, right, of the nodes. So you have to take the XOR of the values of the nodes, right, you can get from here, right, and then each of the 3 components we have to get right for these components, we can say. Then the difference between the largest XOR value and the smallest XOR value is the scope of the pair. But it is not that you have to find how you are going to find the XOR, right? It's you to find all the XOR, but the XOR should have the minimum score. So what we need to do, we have to return the minimum score of the possible edges, that we will understand. So if you have gone through my previous video, you have understood a lot of concept behind that, what I talked about. But still, if you're not gone, let's understand here. So as you can see, we have given one example here, right? If you go through there, you will see one example. What the example is saying that, for example, let's say 3 components have the node value, means 3 components they have. One is 4, 5 and 7. So these components are connected. Let's, for now we can understand like this. Okay, so this is one component, then we have 1 and 9. So we can say this is another component. Then we have 3 is connected with 3 and 3. So these 3 connected components we also have. Okay, means this is one component, this is another component, and this is another component. So total how many components we have? 3 components we have, right? Can we say that? Now once you have all these, so that it is saying that the 3 XOR values are, if you will get the XOR value, means for the first XOR, if you will find the XOR of this value, what you will get? 4 XOR 5 XOR 7. It will give us 6. For example, it is saying that we will get 6. Then 1 and 9 we have, so 1 9 will take, and it is giving what? 8. Then we have 3 3 and 3. Can we say that all of 3 XOR will get what you call 3, right? And now we can say this is your largest and this is your smallest. So if you do 8 minus 5, the largest is 8 and the smallest is 3. Okay, so you will get 5 as a value. Okay, so this is your score, means you have to find all of the score of all of the component, all 3 components score you have to find, and you will find the smallest one and the largest one. Means you have to track what is the largest, what is the smallest one, and then you have to give you the minimum score, right? How will you give the minimum score? Just do 8 minus 3, you will get 5. Sorry, 8 minus 3, you will get 5, right? So this is your the score. So in this you will find the what you call the value, right? And you will return. Not for this example I'm saying, this is the given example we have here, okay, that I'm talking about. So can I give me one second. So can I say that what we have given this, let's suppose for example we have this tree we have given, that having n nodes we have given, it is a connected and a cyclic, correct? Then we can say each node having a value that we can see in the nums, right? So what is our goal? Our goal is to remove 2 A's, right? What we need to do, we have to remove 2 A's, right? Distinct A's that should be unique of the tree, and then we'll form the 3 components, right? Then we have to take the XOR the value of the each subtree, right? Whenever you will create the 3 component, right? Whatever the 3 component will become, let's suppose remaining, original, or you can so not original, R1 subtree, R2 subtree, right? So all these are the 3 components. So you have to take the values of this tree, right? Means each you have to do XOR values, sorry, you can say XOR values of the components you have to find of each subtree, we can say, and then we'll return the minimum possible score that we can get from what? Max XOR value minus mean XOR value, right? And that will be our score, and that we have to return it. So can I say that we will try all pair of A's removal, right? I can remove this one or this one, as you can see the red, or all other possible pairs. It is not mandatory that you will remove this one or this one, right? As I told you, you can remove this one and this one, you can remove this one and this one, right? Or you can remove this one and this one, okay? So your purpose is to create 3 component, right? And that we can make how? By trying all the pair of A's removal. Let's suppose we have given these pairs, so you can choose these 2 to remove, you can choose these 2 to remove, or you can choose these or these to remove, right? Means it's all depends on you, right? But we have to try all the pairs, right, of A's removal. But that will be our program become slow, because you are taking O of n square, right? So if you take O of n square only to try all the pairs of the A's removal, right, that would be slow, and we can say it's become O of n square, it will be slow. So what we will do, instead of doing this, right, what we should do, we should use DFS. Are you understanding? Means if we'll try all the pair of A's removal, at that time it will be very slow, or too slow, you can say. That will give you O of n square only for trying all the pair of A's removal, right? But for that, if we'll, instead of using this trying all the pairs, right, what we will do, if we'll use the DFS to compute the total XOR, right? Total XOR, if you want to find that, right, then first of all what we will do, we'll compute the what you call, let's suppose total XOR, right? And then we should do what? We should record the subtree, that 3 components we have given, right? So all these 3 components is nothing but a subtree of the tree, right? So we will record all the subtree XOR for every node, right? Means we can say, let's record all the subtree what you call XOR, right, for every node. Can we say that? Then in the third, what we will do, then we'll iterate over all the pair of subtree, and then we'll check the remove the affected tree, we can say, right? That we will do through the DFS method. Understand? I hope you understand, right? We will not try the O of n square, we will not try the O of n square, but we'll try the DFS, and the DFS will use first, we'll find the total compute of the XOR, and then we'll record all the subtree XOR for every nodes, and then we'll iterate over all the pair of subtree, and then we'll check how we are removing the affects the tree, right? So So what is our observation, right? So our observation is this tree, let's suppose for the tree is having n-1 edges, that we have understood, in which we have to remove 2 edges, right? And we have to split into 3 connected component, and these components nothing but subtree, right? Let's suppose subtree, what I'm calling multiple tree and tree, right? Let's suppose this is a tree you have, right? 0, 1, 2 and 3. If I will remove this one, right, means this remaining, this is a subtree and this is a subtree of the original tree, correct? And that is why saying we have given n-1 edges. Out of these 2 edges we will remove, right, and will make 3 connected components. These components are nothing but the subtree, right? Then we have to try every components XOR that can be used for you can say full tree XOR, and that is our total, correct? Means if we'll find the subtree XOR of the remove components, we can get it, right? This is your full subtree, right? Means we have to try full tree XOR, right? And out of that you will remove the XOR of subtree, which is a remove component, right? I hope you understand, right? Let's understand the code and we'll do dry run.
Play from the booth.
Okay, so let's understand the code here. Okay, so very first we'll define these things out. So just ignore for now. Let's start from the line number 8, that function we have given here, right? So from where we will start. So let's suppose we have given nums, we have given s, we have given. Can we take here nums? So nums will be, let's suppose we have array like, okay, so in this array we can take, let's suppose we'll take 1, then we'll take 5, then we'll take 1, 4, 5 will take, and then let's 11 will take. Okay, 1, 5, 4 and 11. Okay, so these are the nums element we have, right? Means these are the nodes we have. So what are the nodes is there? Call 0, 1, 2 and 3. Okay, these are the index and these are nothing but our nodes. Can we represent like this nodes? Now let's suppose we'll take edges. Okay, so for now I'll take edges. Let's take edges. Okay, so these edges are, let's suppose we have 0 and 1. Very first 2 node we have, right? 0 and 1 at index 0. Then we have 1 and 2. That is why I wrote the node, so you can understand, right? Then we have 1 and 2 will take, right? And then the third we have 1 and 3. Now you can understand, right? The nodes we have given is 0, 1, 2 and 3, right? And the edges we have is 0, 1, 1, 2 and 1, 3. 0, 1 means the very first is this. Let's suppose if I'll write into the graph, how will represent in the tree, right? Let's understand the tree diagram. Okay, so if you write the tree, it will come, let's suppose give me 1 second. I'll take here, let's suppose I'll take this one. Okay, so let's suppose we have very first node is 0 and 1. This is 0 and 1, so I'll take 0 and there will be 1. Can we take this? So if this is 0 and this is 1, we'll make a node like this, right? And we'll say this is a node. So this 0 node having value is 1, and it is saying what here we have is 0 have 1, let's suppose, and these 5 have not 1. This is 1, right? What I'm trying to do here, give me 1 second. Okay, so this is 0 and this is 1 and this is your 5. Can we say that? Okay, yeah, so very first node is 0 and 1, so we can 0 and 1 we have connected this, and we'll take this value here. Okay, then we'll have 1 and 2. From 1 and 2, let's suppose we'll go like this, right, to here. Okay, can we say this having value is 4? Here we'll take value 4. You can see the here, right, nums we have 4. Then next we have 1, 3. So this 1 will get joined at, let's suppose here, this is your 3. So these are the nodes we have connected each other. Can we say that? And for these 3 we have is 11 point. Can we say that? Right? very first what we need to do, we will build the urgency list. Very first what you will do, you will build the urgency list. So urgency list, let's suppose we'll create, right? How we are going to create? We'll create through, let's suppose we'll go with the all the index value, right? So index is nothing but, let's start from 0 to n-1, right? So this is now nums node start from 0 are going to 3, right? So we'll take 0 to n is nothing but 3, and we will initialize each you can say tree at I, let's suppose is nothing but, let's suppose tree at I. So tree at 0, can we say tree at 0 initially will set these two value, right? So you can take these two value. Okay, so at 0, right, what we have, some value is at 0, right? So at 0 we'll add 1. What we are adding? 1. So we'll say it is 1. Similarly at 1, what we are setting? Value 0. Okay, for the first processing of the edge, when edge is 0 means this is from these edges will get these edges, right? Will get like this. Okay, and for edge at 0 will store here like this, okay, on the tree. Similarly we'll go with the next edge. Next edge is what we have, from 0 to 1 we have already stored, means 0 have one edge, that is this, right? Then we have 1 2 means 1 to 2. So at 1 we will store again 2. So we'll say remove the we'll remove this one, okay, and we'll say we have another 2 is 1 is connected with the 2 because we are processing now this. So at this what we will get, is at 0 we have is 1, and we'll add is at 1 as a 2, so we'll add at here 2. Can we say that? And then is at 1 we have 2, so we'll say at 1 at 2. Give me 1 second. At 2, can we say that? So tree at 1, tree at 2, and at 2 we will store what? 1, right? Because we are processing this one. So is at 1 we have to store is at 0, so we'll get here. Now we'll process this is 1 3. So when we are going to process 1 3, right, what we need to do, we'll get is at 0. Is at 0 is 1, right? Means we are talking about this is this node, this index of the edge at tree, right? So is at 0 is 1, so we'll add is at 1 is 3, so we'll add here, right? What we need to do, leave me here from now, and we'll add 3. So this will be your tree at 1, right? Now we have what is at 1 is 3, right? So what we have to do, 3 add, what we have to add 1. So add 3 we have to add 1. So we'll take another tree at 3 and we'll store what is 1, correct? So this will be your urgency, what do you call, we are building the urgency list, right? So let's understand further. We will create the XOR, subtree XOR. As I told you, if you know the subtree XOR, you can easily find the total XOR, right? So what you will need to do, you will create subtree XOR with the same number of nodes, right? And there will be time in, tour out, okay? Because we are going to use, if you have seen the first part of video where we have talked about Euler tour timer, right? Tour timer, we have used this concept, right? So this concept saying we should have tour in and tour out details also, okay? So these three array we will use, right, to compute the timer, right? Timestamp you can say. So let's suppose if I will start the compute, right? We want to do the DFS, right? Further, so we'll do the DFS to compute the subtree XOR and the entry and exit time for ancestor check, right? We'll do. So we'll use this DFS 0, -1 and time, right? So we will compute JOR at u, means JOR of subtree rooted at u, right? We'll find, and then we will have the size at u, means number of nodes in the subtree we'll get, and then we'll find the direct parent of u, okay, through this DFS. Means we are trying to find we are trying to use the DFS to compute the subtree JOR, right? And its entry and time in the ancestor check. Means we have to find the direct parent of u. Who is the direct parent of u? That we will assign. Then we'll find the JOR at u, means the JOR of subtree which is rooted at u, that we have to also find, okay? So let's understand the how we are going to implement this DFS, okay? So this DFS we will compute here, right? Give me 1 minute, okay? So as you can see, we will provide the node parent nums, right? And we'll find the entry time of that node at time in at node, that value will update. Then we have the subtree JOR value at this node, and you will start from here, right? And you will get all the tree at node, right? You will find the neighbors, you will check if it is not parent, you will do the DFS, right? And you will do the update the JOR value, right, at the given node, and then finally you will find the timer. So like this we'll keep going that, right? Means we are going to find all its node and parent until the neighbor is not parent, right? We'll do this, this loop will keep going there, okay? Means each component we will find its a JOR, right? So let's suppose if we will start DFS at node 0, right? Means very first, let's suppose we are starting the node at 0. Can we say that when we are starting the DFS at node 0, it means the node is 0, right? And parent is, let's suppose we don't know for now, so we'll take -1, right? That we have seen, and the nums will pass, means 0, -1, and this because the 0 is the parent, the root node, right? And it doesn't have any parent, so we'll say the parent is -1, there is no parent is there, right? So from 0 we'll start from the root node, right? So let's suppose we'll do JOR, right? For now, for this JOR. So let's suppose we'll say we go for the subtree JOR, we'll find what nodes at 0, right? Means nodes at 0, what we have is 1. I am talking about from where we got the nums. Remember, we had nums at 0. From there we'll get nums at 0, what we have is 1, okay? So we'll get the JOR of this value. Then what we will do, we'll move to child, right? We can move to the child. Next, what we need to do, then we'll do at node 1. When we was at node 0, we got the JOR value, we are getting 1. Then we'll move to the child, right? What is this child? Let's suppose child is node 1, right? So now understand, if we'll take so very first what we have done, we have find or the node 0, then we'll find the node at 1, right? So let's suppose now we'll take at node at 1, okay? When node is 1, okay? Give me 1 second. I don't know what happened to my mouse, it's moving here and there automatically. So very first what we will do give me 1 second, I'll start again. Okay, so very first what we have seen at node 0, right? When at node 0 was there, right? Means what are the nodes are there? We have given 0, then we have it was 1, right? And then give me 1 second, I forget. So first it was 0, right? Then we have 1, 1, and then we have it was 2, right? It was 2, and then it was 3, like this we have, okay? So this value was 1, then we have 5, then we have 4, and this is 11. Just think. So very first, when the nums was given, I'll write here nums for understanding. Nums we have is 1, 5, 4, and 11. This was our example, yes. 0, 1, 2 and 3, and we had some aces was there, right? So when I'm talking about when node is at here, means we are talking about this, means this node we are talking about. Okay, give me 1 second guys. So let's start with here. So when we are at here, so we'll do the DFS at node 0. Can we say that? So when we start DFS at node 0, we'll take what? This XOR node. Can we say that? XOR node will take, and this XOR node is nothing but what? 0. And its parent is what? -1. That is why we will pass parent as -1. So node is 0 and parent is, what is parent is -1, right? So that is why you have seen the previously that when we call very first time after creating the urgency list, what we have used? We have used node as 0 and parent as -1, and this is our nothing but the new nums we can say, right? So we will provide these nums here as for now. New nums means we are providing these nums. Okay, this is not new nums, it's really nums. We are providing all these nodes value. Okay, so we'll start from the DFS from here, 0 node, root node, and when we find the XOR of this value, right, means we are trying to find what we have is 1, as you can see here, right? So what is node at 1? We are getting is a 1. So you can see also here, right? Means node value will get. Then we'll move to the child, right? What is our child? Is 1. Now we'll reach the pointer here, right? We'll do the DFS means control. DFS control will move here, right? So at node 1 means when we are at node 1, we are at node what? When we are at 0, we did this one. When at 1 we are here at this location, what will happen? We'll find the XOR at 1, right? So we'll do same thing here, XOR at 1. So XOR at 1, what we have is 5. You can see here, you can see here also, right? What we have? 5. And you can see here also what we have? 5. Means nums at 1 we got is 5 and we written here. Now we have to move to its child. So there is 2 child is there, 2 we have and 3 we have. Let's suppose we'll move to node 2 here. Okay, so when we move to node 2, we'll do the XOR at where? At 2. So when do XOR at 2, it means what we will get here? We'll get the 4, as you can see here. So we are seeing here also. Okay, it means we got the what we got here? We'll got the parent, right? So what we'll check also parent at this means if we will keep moving, right, means never node not equal to the parent. If it is not equal to parent, we'll keep doing the DFS like this we are doing, right? So we'll keep doing this one, right? So we'll see the XOR will do the never node, right? So when we'll do the never node, right, we will keep going, we will keep doing this one, right, until it is not equal to the parents. Let's suppose we'll find the parent at this. So let's suppose we'll say what is the parent of 2. So we'll say parent of 2 is 1 here. Can we say that? Because this parent we can get 0. We can get this parent is a 0, but 0 doesn't have any parents. So for now we'll understand, we'll not do at here, we'll keep moving and we'll check until we reach here the children, right? So when we'll move to the one's children, that is 2, right, it means we want to find its parent at 2. Let's suppose what is at parents at 2? Parents at 2 is nothing but 1. So we will say this is 1. It means we will return to 1 back. Can we say that? It means if I'll find, means we are trying to go here, right? If it is not the parent, right? Okay, means we will do what? XOR at 1. Just understand, XOR at 1, and we'll apply these things, right? If it is like this, what we need to do? We have parent. If we have parent, we'll apply the XOR. So we'll say XOR at neighbor. Who is the neighbor? So this is your parent node. Parent node is 1, right? And child node is what? Is 2. So we'll provide 2 here. So here, what will come here? We'll say this will become XOR at 1 is 5, then we'll take 4, right, and this value will give you 1. We know that, right? Now we'll move to the control at 3. Similarly, that we have done this part, right, from here to here, this part will repeat. Let's say at 3 we will find the XOR, right? XOR at 3, let's say. XOR at 3 is nothing but 11, as you can see here. You can check here also, right? So XOR at 3, we got the 3, 11, and XOR at, so what is the parent of this, right? Now we have to find the parent. So parent at 3 is nothing but 1, means we will return back to where? At 1 here. So we will apply this formula. So XOR at 1, what? XOR at 1 will do, and XOR at 3, correct? So this is nothing but 1, and this is nothing but 11, right? What we will get? 10. Now we'll return back to where? At here. So from here we'll go back to here, right? Means XOR, so the control from 1, it's returning to 0, right? So we'll say let's say XOR at 0, and we'll do similarly XOR at 1. What we will get here? We'll get 1 XOR 10, and we'll get here 11. Can we say that? So like that we'll keep computing this, right? And if you observe, we are able to calculate all the XOR, subtree XOR, right? So like this we'll keep doing that, and we'll find the XOR. So can I remove this? Give me 1 second. This is only for your understanding, guys, okay? So I hope you will like this video, because I'm trying so hard. Okay, so it's really time wasting. Sometime I'm thinking, but no, I'm helping you so you can understand. Let's see the final computed what will happen, right? So you have seen 1 we have taken, 3 we have took, right? And then what we call at 3 we have received some value, right? So 3 was this one, so XOR at this value we'll got. So let's suppose if we'll summarize this, not we'll do like this. So we'll keep at one place, okay? Let me remove this one also. I hope you understand, okay? So let's suppose all the XOR I will keep at one place, okay? So these XORs are what? 11, then we have 10, then we have 4, and then we have 11. Can we say that? And the size that we have seen is 4, 3, 1, and 1. And what we have at parent? At parent we have seen we have -1, 0, 1, and 1. These are the parents, right? So we'll try now all the its pair is to remove, right? Let's go back to the code. Understand what happened? Give me 1 second. Okay, so we were here, okay? So once you do the DFS, your subtotal, your subtree, you have got the data, right? From here we have prepared the subtree XOR at 0, 1, 2, 3, all the nodes. So very first you will initialize total XOR from at node 0, right? And we have to track the mean score also. So very first we'll find the infinite value of the integer, and you will put into the mean score, right? And then we'll try all the pairs of a's to remove the what you call edges, right? The edges. So we will skip node 0 and we'll start from I 1 to n-1. Can we see that? So for that, to iterate that, you need two for loop you need, right? So let's suppose, give me 1 second. So let's suppose we are trying to remove, right, the edge, right? So we'll try to remove all the pair of A's, right? And we'll skip the node 0 first, right? We will skip node 0 and we'll start from where? At I equal to 1 to n minus 1, right? That is why we are taking the for loop this and this, right? So very first for loop is we are starting from 1 because we are skipping the node 0, and then we'll start from the node 1 and we'll go to the last node, right? As we have seen, right? So very first, let's suppose the pair we will use I equal to 2 and j equal to 3. Okay, so these two pair will take, means I'm going to remove these things. Okay, means we'll take the two pairs, that is start from 2 and 3. Can we say that? Means all pair we will try like that, right? We will not do randomly that we have seen in the example, but in this way we'll try all the pairs. So very first, if we'll check one is the ancestor of other, right? So we'll provide a function that will check is ancestor. If is a ancestor means is it parent, right? If it is parent, ancestor means, let's suppose this is here, this is your parents and this is your grandparents, right? There can be many grandparents will be there, right? So here can we say that this is this as ancestor, right? I and j, between I and j, right? If this is the condition, right, it means this part will return you true. Okay, where you can find x and y, right? Once you will find x and y, right, you can find the g also. Okay, because subtree at XOR at j, we will find the value x, right? Then we will find y, and then you can also find, you can track this value, right, g. And to find the score, you need to find three things, right? X, y and g from three components, right? And x component, y component, j component, you will find it, right? This is your remaining part, right? And then you will track the mean score. Once you will find the mean score, right, you can return the mean score. So these are the possibilities that you will try, right? You will try from different subtrees, right? Let's suppose x is nothing but let's suppose XOR at 2, that will give you 4, right? Then y, let's suppose we'll have XOR at 3, it give you 11. We have seen the example, right? And let's suppose we have XOR at what, 0, and then we are taking XOR at 2, and that XOR at 2. Can we say that? It means it will come around 11, then 4, right? And 11, 4, and we'll take this 11, right? So it will also come 4. Yeah, so this and this is same, so you can say this is 4. Okay, so like this we'll prepare x, y and z, right? So we can find what, the max is 11, we can say, mean is 4, we can say, and so the score will become what, 11 minus 4, we know that will come 7. So we will find all these three in all of these logics, right? And you can track the mean score, right? You can similarly, you can track for we have take for I equal to what was that, 2 and 3, right? When I was 2 and j was 3, when like this, then we have found that score, right? That score was coming what, 7, right? Now let's suppose we'll take I equal to 1 and 3, right? So when I is 1 and j is 3, then what will happen? You will check 1 and 3, is this ancestor? Yes, it is true. Then what will you find? You will find the XOR. You will find the x, y and z. XOR at what, 3. XOR at 3 is nothing but 11. Similarly, you find XOR at what you call 1, and XOR at 3. You will get some value, right? This is your 10, this is your 11, we will get 1. Similarly, from here you will get what, XOR at 0. You will say, why you are so hurry? Because I am seeing this video is already too long, so most of the viewer will not watch, so it will be waste, right? So it will come what, 1, right? And so you will find the max again. So max will become, let's suppose 11 here, then y the mean will become what, 1 here. So you can find the score will become what, 10, right? So the answer we have to find, mean is, let's suppose 7, answer and 7, whatever come the previous is coming, let's suppose 7, it is coming, answer is this. which is minimum. The 7 is the minimum, right? So we'll keep doing that, right, until you will find the minimum, right? Comparing all such pairs. Just for example that I am showing, these are the examples. You can find, you can put the value, you can try by yourself. Okay, when you are using the notebook, this is little smaller one, so I'm not able to add all the values, right? So I'm trying to give you the information, so how you can build the logic, how you can dry run the code. Okay, so you continue comparing all such pairs and find the result. Let's suppose the result will come a mean score something, it will come 2. Okay, so that will be your answer. Okay, like that we will keep doing that. Okay, so if you talk about the what you call, give me 1 second guys. So if we will talk about the intuition, means we will remove the 2 edges and we will split into 3 sections, right? 3 component, and for each component has a XOR. So to find the score, we have to find the max between XOR 1, XOR 2 and XOR 3, and we'll find the max and min, and we'll find the score, and we'll try all the valid edge pair to remove, and we'll use DFS, right? We'll use the DFS to pre-compute the subtree XOR, and parent relation will use the each ancestor method, as you can see here, and will handle the overlapping components correctly. So I hope you will like this video, guys. This is just for deep dive, and I've already uploaded the first part of the video. I'll suggest please watch both of this video and let me know in the comment section that you will like this video or not. If any enhancement needed, any suggestions you have, let me know in the comment section. And thank you for today giving me your time, and I'll see you in the next one. Please support ExpertFunda by liking and subscribing channel. Also write you like this video or not. That will motivate me to create a better videos for you, and I'll see you in the next one.